Now let's solve part C. We want to know what the critical velocity is. The critical velocity is going to occur when there is no string tension at the top. In other words, the only force that's going to be acting on the object is going to be its weight when it's up at the top. So let's sketch a free body diagram up there. Let's take toward the center of the circle the direction of the acceleration as the positive direction. Then let's write Newton's second law. The acceleration is v squared over r, where v that we're looking for now is the critical velocity. The only force that's acting is in the positive direction. That's the object's weight. Now what am I looking for? I'm looking for the critical velocity. So I want to solve this equation for the critical velocity. And I want to write the weight as mg, because you're going to see that if I do that, the m's are going to cancel each other out. And the critical velocity is going to be independent of the object's mass. So let's solve this equation for v crit. And now let's put in the numbers. And let's substitute them into the calculator. I find that the speed, the critical velocity, is 3.16 meters per second. That solves this problem. Let's go on to the next problem. A toy car has a mass of 3 kilograms. The car must complete a circular loop whose radius is 40 centimeters. What minimum speed must the car have at the top of the loop so that it will not fall? We're looking for the critical speed of this car. So when it gets to the top of the loop, the only force that's going to act on it is the object's weight. Now, while it's at other points of the loop, there is a normal force. The track pushes the car into the circular path. If the track weren't there, the car wouldn't go in the circular path. But at the very top, there is no force acting at the critical speed except the object's weight. And the object is moving in this 40 centimeter path. So let's figure out what that minimum speed is. Let's begin by sketching a free body diagram. At the critical speed, the only force that's acting is the object's weight. Let's choose the positive direction to be the direction of the acceleration, which in this case is centripetal acceleration. The direction is going to be towards the center of the circle, and that happens to be the same direction as the weight. I'm going to call down the positive direction when the object is at the top of the track. And let's write Newton's second law. The acceleration is equal to the net force divided by the mass. Now there's only one force in this problem. It is the weight. The acceleration is the centripetal acceleration. So I'm going to replace acceleration with v squared over r and the net force with the weight. And I'm going to write the weight, if you'll permit me, as m times g. So you see that the mass is going to cancel in this. It doesn't matter whether I have a Mack truck or if I have a Burlington Northern Santa Fe railroad train, or if I have a Hot Wheels car or anything else. If I've got a track that's sufficiently strong, the critical speed is not going to depend on the mass. So now let's substitute in the numbers. I encourage you to work in a consistent set of units. So if you have numbers in centimeters, then you need to convert them into meters. Let's put the numbers into the calculator. I get that this toy car must be going at least 2 meters per second when it gets to the top of the track if it's not going to fall down. The second part of lesson 49 deals with electric power. I want us to recall some things about voltage and current and power. First of all, the definition of power. Power is defined to be the rate at which energy is transferred. It is work divided by time, or energy divided by time. The unit for power is watts. A watt is a joule per second. In an electric circuit, the source of charge motion is some seat of EMF, some battery, some generator, something that's able to pump the charge around the circuit. And we measure the electrical pressure in a unit that's called volts. Remember, voltage is equal to a joule per coulomb. It's energy per charge. When the charge moves around the circuit through wires, through resistors, through motors, through whatever electrical devices that the charge passes, then the rate at which the charge moves through the circuit is called current. Current is equal to charge per time, and the unit for current are amperes or amps. An amp is a coulomb per second. Ultimately, what we're interested in doing is converting this electrical energy into other forms of energy that are useful to us. I use electricity to light up a flashlight or to turn on the lights in my room. I could use electricity to heat my home, to make it warm in a room that's cold. I could use electricity to turn some object that's useful for me, a motor of some sort. I'm going to be taking electrical energy and converting it into other forms of energy. And the rate at which that happens is called the power, the electrical power. And ultimately, when I pay my electric bill on a monthly basis, what I'm paying the electric power board, ultimately TVA, who has the generators at the power dam that are taking mechanical energy in the form of water rushing through a turbine or steam rushing through a turbine, and then elevating the energy in those charges in the wires. What I'm paying them for is electrical power, and the rate at which that energy is transmitted through the wires is something that I'm finding useful in my own appliances. Let's figure out what electrical power is. So if you'll bear with me, we're going to write some things down. Suppose that I took current and multiplied it by voltage. Let's look and see what the units would give us. We're talking about an ampere times a volt. An ampere is a coulomb per second, and a volt is a joule per coulomb. And now look what happens to the coulombs. They disappear, and I'm left with joules per second, which is the same thing as watts. And what I've just done here is a hand-waving argument to try to convince you that electrical power is equal to current times voltage. And if we use symbols that we've used before, P for power, I for current, and V for voltage, then we have ourselves a formula for electrical power. P is equal to I times V. That's a very important formula. That's one that you need to memorize and be prepared to use. There are two other forms in which a electrical power equation is useful, and these forms come from Ohm's law. So let's recall Ohm's law. I is equal to V divided by R. If I take this result for I and feed it into the power formula, then I'm going to get the second of the important formulas for electrical power. So let me substitute I into the power formula from Ohm's law. And now V times V is equal to V squared, and we get our second formula. P is equal to V squared over R. This is the second of three important formulas for electrical power. Now let's figure out what the third one is. So what I'm going to do is I'm going to take Ohm's law and solve Ohm's law for V instead of for I. And now what I want to do is I want to go back and substitute this V from this second form of Ohm's law into the original power formula. So I'm going to take this V and feed it into the power formula, and I'll get P is equal to I times V. But now I'm going to write V as I times R. If I take I times I get I squared, and we end up with our third important form of the power formula. P is equal to I squared R. These three formulas for electric power, combined with Ohm's law, will go a long way to help you solve problems involving electric circuits. You'll see that some of these are more useful than others for particular situations, but in general, you should look at the information that the problem gives you and then choose the equation that has that information in it in order to help you solve the problem. Here are a couple of examples. A 12-volt battery is connected to a 3-ohm resistor as shown. What current flows through the circuit? How much power is provided by the battery? How much power is used by the resistor? And how much energy is expended in 1 minute? Let me remind you that this script E stands for EMF, or electromotive force, and in our parlance, this means the same thing as voltage. So E and V mean the same thing. Let's do part A. How much current flows through the circuit? Well, we know what the voltage is. It's 12 volts. And we know what the resistance is. It's 3 ohms. We can apply Ohm's law to figure out the current. Now, I've written Ohm's law in terms of EMF instead of in terms of V. So I is equal to E over R. And now I put in the numbers. E is 12 volts, R is 3 ohms. I'm going to get a current of 4 amperes from this. How much power is provided by the battery? The current that's flowing through the battery is the same as the current that's flowing through the resistor. So there are 4 amperes flowing through the battery. The power is going to be equal to the current times the voltage. The current is 4 amperes. The voltage is 12 volts. 4 times 12 is going to be 48 watts. How much power is used by the resistor? Well, the resistor has a current of 4 amperes flowing through it, and its resistance is 3 ohms. So I'm going to say that the power that's dissipated by the resistor is equal to I squared R. 4 squared times 3 is 16 times 3, which is also 48 watts. And this makes sense. Conservation of energy tells me that whatever energy is expended by the battery is going to be dissipated by the resistor. Now I'm assuming I have ideal connecting wires, and so there's no energy lost to heat in the connecting wires, which is a pretty good approximation. And for the most part, that's going to be how that things are on the AP exam. Last part, how much energy is expended in 1 minute? Now to solve this, I have to remember my definition of electrical energy. Energy is equal to power times time. Because power is energy per time, then energy is going to be power times time. We've already found that the power is 48 watts, or 48 joules per second. The time we've got is 1 minute, which is the same as 60 seconds. So let me put these numbers in. I'm going to say that there's some units that cancel. The seconds cancel, the minutes cancel, and I'm going to be left with joules. So I find that I expend just under 2,900 joules in 1 minute. Here's the last example. A 40-watt automobile headlight runs off a 12-volt car battery. A, determine the resistance of the headlight, and B, how long must the light be on in order to dissipate 2,000 joules of energy. I think I would find it helpful to sketch a circuit diagram in this. I've got a 12-volt battery and a 40-watt bulb. I don't know what the resistance is, but because I know what the power is, I can use one of the power formulas along with this voltage to figure out what the resistance is. Let me make a note here about the power of light bulbs. Bulbs' powers are rated at certain voltages. And I have seen twisted physicists turn AP problems into confusingly worded situations that are unkind to students who are trying to demonstrate their knowledge. So whenever you see a power rating on a bulb, you need to be aware that that power rating occurs at a certain voltage. And the voltage for this particular bulb is 12 volts. On the other hand, for a lamp that's in your house, if you have a 100-watt bulb, then that bulb is rated at 120 volts. And if the voltage changes, then the power rating is also going to change. So just bear that in mind when you see problems like this. Now we're trying to figure out what the resistance is. And this bulb is operating at its rated voltage. Let's invoke the power formula that says the power is equal to V squared over R. Since we know V and since we know P, then we can figure out what R is. Let's solve that equation for R. And now let's put in the numbers. I get that this resistor, this bulb, has a resistance of 3.6 ohms. Part B, how long must the light be on in order to dissipate 2,000 joules of energy? Well, we know what the energy is, 2,000. We're trying to figure out what the time is. We know what the power is also. It is 40 watts. So let's take the energy formula and work it to get the time out of it, and we'll figure out what that time is in seconds. And if we need to convert it to a more appropriate unit, we can do it after we figure out how many seconds that it takes. So power is equal to energy divided by time. That must mean that time is equal to the energy divided by the power. The energy is 2,000 joules. The power is 40 watts, or 40 joules per second, which is equal to 50. It takes 50 seconds for this power to be dissipated. Recapping this part of the lesson, we found that there are 3 important equations for power. Those 3 equations may be written in terms of voltage as V or in terms of EMF, E. Other equations that are important in this are going to be Ohm's law and the definition of energy. These formulas will get you a long way. One caveat is don't confuse the EMF, a script E, for energy, which is a capital E, or electric field, which is kind of another way of writing E. There are a whole bunch of E's that are flying around. I am so sorry for the difficult fact that there are several different symbols that are very close to each other and that are related to each other, but that's just the way that it is, and it's not going to change before the AP exam. So for now, That's it.